Hi there, welcome to Telefunken. Today we're going to be talking about and showing you how to service the keybed from the keyboard of the original Korg MS-20 analog monophonic synthesizer. The focus today will be on the keybed's electrical function. That is, the switch contacts and the various resistors form the array that determines the control voltages sent to the oscillators. We'll talk a little bit about the various keyboard styles found in vintage electronic synthesizers, and the information provided today may give you enough detail to set about servicing your own keybed on your own vintage synth. The keys in a vintage monosynth are the primary interface between the player and the instrument itself. By pressing a key, the player is selecting the pitch and determining the control voltage that goes to the voltage-controlled oscillators. The player is sending a note on trigger when they press a key, or they're sending a note gate, and sometimes both, as these signals are not identical. These keyboard functions are accomplished through the use of either 1, 2, or 3 bus systems, and these bus systems are in turn connected to the circuitry that controls the relevant functions. Vintage synths such as the Korg MS-20 lack velocity or aftertouch. There are two main pitch control voltage standards used in vintage synthesizers. The first, the so-called linear scale, is the volts per octave, the most common, whereby the voltage associated with any given pitch increases linearly with the pitch as measured in tones or semitones. Each volt increase in control voltage corresponds with an octave increase in pitch. This corresponds to an 83.3 millivolt increase in control voltage for each semitone. The other less common scale is the hertz per volt standard, which was utilized by Korg, some of the early Yamaha synthesizers, and other manufacturers such as Paya. In this case, the exponential scale, the voltage doubles with each octave, as does the frequency as measured in hertz. Typically, this is roughly a 55 hertz increase in frequency per volt. The way this plays out practically is shown on this graph. Here you can see the 88 keys on a piano keyboard laid out on the x-axis. On the y-axis, we have the control voltages that might be associated with each of these keys. You can see with the volts per octave scale, if we set C3 at 2 volts, we see that the voltage tops out around C8 at approximately 7.5 volts, while the hertz per volt scale increases exponentially, climbing to greater than 30 volts at C8. These higher control voltages at the higher registers can be a liability for synthesizers that utilize the hertz per volt standard, as many operational amplifiers used in these earlier synths are using a positive and negative 15 volt power supply. They have difficulty managing with voltages that are close to their positive supply rail. There's also more than one trigger standard for vintage synthesizers. The V trigger, the most common trigger, is the voltage trigger. In the note off state, the voltage is low, 0 volts, and in note on, it rises somewhere between 2 and 10 volts. In most cases, usually plus 5 volts. This type of system in many cases can respond to audio triggers such as snares and the like, which will trigger a synthesizer and can be used as a V trigger. In the case of the Korg MS-20, it utilizes a system called the S trigger. S is short for switch or short circuit. However, in this case, we have a situation whereby the voltage is held high, around plus 5 volts in the MS-20 in the note off state. Then when the note is played, the voltage is reduced to 0 volts. In some synthesizers, this is accomplished by shorting the trigger signal to ground. In this case, it is not a short in the Korg MS-20, and this S trigger may be incompatible with some other systems. There's quite a variety of keyboard mechanisms that can be found in vintage synthesizers. Because the expertise required to design and manufacture mechanical keyboards is quite different from that required to design and manufacture electronic circuits found in synthesizers, most synthesizer manufacturers farmed out the design and manufacture of their keyboards to third parties that would manufacture them on their behalf. Pratt Reed was one such keyboard manufacturing company. Established in 1798, Pratt Reed is one of America's oldest companies. Their original line of work was taking elephant ivory and making piano keyboards. What's shown in the photograph is a portion of a mechanism from a Moog 951. This is a 3-bus bar keyboard mechanism. The contacts consist of bus bars, which are the 3 heavy bars that are going from left to right in the photograph, and springs which protrude through the printed circuit board. These springs are connected to rubber or soft plastic levers which are pulled towards the top of the photograph and contact the bus bar, completing a connection. You can also see in the photograph light blue or gray resistors which are connected in series. We'll discuss those in a moment. Another Pratt-Reed mechanism from a Moog, in this case a mini Moog, is shown on this slide. And again, you can see the plastic actuators which bring the springs into contact with the bus bars. Again, a 3-bus bar system. Another Pratt-Reed mechanism, a J-wire mechanism, is shown in this slide. This was taken from a micro Moog. In this case, the J-wires, which are the vertical lines which are shown behind the bus bar towards the top of the photograph, are made to contact the bus bar when they're pressed against it by the cylindrical elements which are shown towards the middle of the photograph. The white integrated circuits shown in this photograph are actually resistor arrays which perform the same function as the discrete resistors shown in the previous photograph. That is, they form a voltage divider system which determines the control voltages across the range of the keyboard. Another Pratt-Reed J-wire system is shown in this slide, in this case from a Prophet 5. Again, we can see the single bus bar towards the top of the photograph and the individual J-wires running vertically, which are connected to their actuators, which press them against the bus bar. We can also see in this photograph a number of diodes, and this system utilizes a diode array rather than the resistors in series, and there are implications for this in terms of determining the control voltages that we'll address in a subsequent slide. Another Pratt-Reed mechanism, also from a sequential circuits product, in this case a later Pro 1 monophonic synthesizer, is the membrane keyboard. Although at the time considered to be an improvement over the J-wire system, this system has become to be less highly regarded and less desirable relative to the J-wire systems that were also utilized in the earlier Pro 1s. Not to be outdone by their American counterparts, the Japanese were also busy manufacturing keyboards as well. In this example, a Matsushita keyboard from a Roland SH09 is shown. Matsushita is a company that may not be a household name in North America or in Europe. However, it's subsequently been bought out by Panasonic, which certainly is. In this example of a 2-bus keyboard, we can see the 2 bus bars towards the top end of the photograph, and you may be able to make out 2 layers of reeds which come into contact with the bus bars when pressed against them by the actuator mechanism shown at the top. Matsushita also made keyboards for Korg, and indeed they're responsible for the manufacture of the keyboard and the Korg MS-20. And this is an illustration of a keyboard from an MS-20, the Matsushita SK431. Here you can see the key contacts separated from the keyboard mechanism, and the bus bar, indicated with a dotted red line, is actually considerably thinner than those on the previous examples, such as in the Pratt-Reed mechanisms that we've already looked at. The contact surfaces in the bus bar indicated in this photograph are really the business end of the mechanism for the Korg MS-20's keyboard. Dirt or corrosion in these areas can result in either improper note sounding or the absence of any sound whatsoever when pressing a key. Once you've disassembled your keyboard, which we'll show you how to do in a moment, you'll need to clean these surfaces, ideally without contacting them, using a chemical contact cleaner such as deoxit. We'll show you how to measure whether or not you've done this properly, and if you have contacts that are resistant to cleaning, I'll show you how to clean them properly without damaging them. While we're in there, we'll also be examining some of the electrical components that are actually on the keyboard assembly itself. This is the Korg MS-20 schematic diagram, or at least a portion of that which represents the main board including the keyboard, and the keyboard control voltage circuitry is highlighted in red. Being a single bus keyboard, the pressing of a single key generates a control voltage denoting the pitch of the note. Much of the circuitry that's circled here is committed to detecting that key press and generating a trigger signal which is subsequently fed to the envelope generators. The remainder of what's circled is the portamento circuitry, which generates a gradual shift in control voltage when portamento is activated. However, it's only this smaller region here that is actually on the keyboard itself. There are three electrical connections between the keyboard and the rest of the synthesizer, and they're shown on this slide. First, there's the positive rail, which is connected to the bus bar. There's a chassis ground, and then a control voltage out. The keyboard has an array of resistors arranged in triplets. These are precision resistors, 403 ohms, 427 ohms, and 61.9 kilo ohms in value, and they're arranged in such a way as to exponentially divide the voltages across the range of the keyboard. This is considerably more complicated than the type of circuitry that we see in a typical volts per octave keyboard arrangement. However, we'll come to that in a moment. Because of the complexity of this resistor arrangement, it's almost impossible to measure accurately the value of any one of these resistors, which would be the first step in ensuring that there hasn't been any degradation in the electrical performance of any of these individual components. However, we can do our best to measure each of them in situ, and as long as we find that none of them are shorted, we should be in good shape. We can also measure the performance of each switch contact by measuring between the bus bar and either the CV out or the chassis ground as we press on each individual key. This way we can ensure that our cleaning efforts weren't in vain. The analogous voltage divider circuitry found in a typical volts per octave keyboard is shown in this slide. This is the circuitry from a micro-moog or a multi-moog keyboard, in which we have a series of 100 ohm precision resistors, which, because they're in series and because each end of the resistor is attached to an individual key contact, they're essentially isolated from one another electrically, and their resistances can be measured quite readily. Some keyboard mechanisms utilize diode arrays or diode matrices to sense the pressing of a key. In this example, taken from a Sequential Circuits Pro 1, we have an 8021 8-bit Intel microcomputer, one of the first microcomputers that Intel manufactured, which senses the pressing of a key through a diode array and then translates this through a DAC, an AD558, a chip that's still widely available, to a pitch control voltage, which then subsequently controls the frequency of the voltage-controlled oscillators in the synthesizer. It should be obvious that any keyboard that has diodes on the keyboard mechanism is utilizing this type of microprocessor to control the voltage-controlled oscillator. But let's get back to the Korg MS-20. We'll open it up and see what's inside. In order to remove the keyboard from the MS-20, take out the 3 bottom screws from the right-hand side cheek. Take out the 5 bottom screws from the left-hand side cheek, and the 4 screws that are on the back bottom edge, securing the bottom edge to the rear panel. After this, the keyboard assembly should just drop right out if you lift off the rest of the synthesizer from the instrument. Disconnect the control wheel assembly and the connector that connects the keyboard to the rest of the synthesizer. So we're about to take the keyboard assembly off of the chassis, and it's held on with these screws on the back side. So we'll simply take those off. And there we are, keyboard assembly. We'll collect all these screws and lock washers and make sure we don't lose them. Put them in our bag of tricks. The keyboard can be further disassembled to give access to various elements that might benefit from cleaning. Amongst those, the keyboard actuators, which are these little switches that if we press a key, we can see the contact being made. And we need to make sure that all of these are spotlessly clean. So in order to take these apart, one simply removes these brackets and then these screws, and then the contact assembly can be lifted off. go. And here's the assembly. You'll note that it is connected with 3 jumpers and a resistor. I want to be mindful of that and not destroy this resistor. These resistor values are integral in terms of maintaining the pitch of the instrument. And there we have our contacts, the contact surfaces, and we'll set about cleaning all this up. And yes, we can see there are some areas that are much cleaner than others. So, set that aside for the moment. But we're not going to disassemble the keyboard entirely. We're simply going to clean it in its current configuration. We'll give this a scrub in the bath. Although I will see if I can remove this felt strip first. Otherwise it will have to just be dried very thoroughly. But yeah, we'll clean this literally in the bath. And we'll check all these resistor values and make sure that they're exactly what they're supposed to be. So what we have here is the keyboard assembly, or at least the actuators, the switches that form the keyboard assembly. And you'll notice this series of resistors that is part of the mechanism here and the circuitry. And this is outlined on the schematic diagram in this section here, immediately below the power supply. And it's represented only partially in that you see this array of resistors, 403 ohms, 427 ohms, and 61.9 kilo ohms, and a 6.8 K on one end of this array. And these are arranged in series, and then a set of 61.9 Ks going from the switch to ground. And what this does is it sets up a voltage divider circuitry that determines the voltages that are going to our voltage controlled oscillators. And we want to make sure that all of these resistors are within specification, and that the switches are all operating properly, and that we don't have corroded contacts, which could lead to intermittent playing of the notes or inappropriate voltage coming through to the voltage controlled oscillator. So what I have done is I've of course cleaned this assembly, and then I've gone through and made some rough determinations of what the resistor values should be and so on. I won't get into that. And then I've actually measured each and every resistance across either the ground connection, the positive, or the actual key connection, the output from this array, and tallied them all and looked for discrepancies. And I've also measured the resistances of each of these resistors as best as I can while they're in circuit. And they don't give you the exact 403 and 427 ohm values because of the way that they're wired, but rather there's a range of values. And again, the way that they're wired is such that they alternate between about 490 to 427 at the 390 to 427 at the top end. So I have checked all of these resistor values and examined each and every one of the contacts. And I'll give you an example of how I examine a contact. You can place the keyboard assembly in this orientation and get access to the connections here. And currently I'm measuring between the ground and the positive. And if I press any one of these keys, what I'm doing is I am closing a contact between the positive and the ground connection, and that gives me a resistance on my voltmeter, in this case 3.579K, and it's a nice stable resistance, and it doesn't vary at all over time. I'm pressing very lightly, by the way, and I'll give you a slightly different view of the contact mechanism here. Hopefully you can see that there's a very thin wire that is connected through this central bar here. And then there's the very thin metal strip which presses down on that wire, and that's our switch. So these two surfaces, both the wire and this metal strip, need to be very, very clean. And you can see here that there's some tarnish, some corrosion here in spots, and I don't know what that's from, if that's just from condensation and rust, or if over time liquids may have been spilled into this instrument and corroded it. Nonetheless, after cleaning with deoxit, most of these contacts were just fine and operated properly. However, one or two gave me a little trouble, and I needed to give them extra attention. And this is the worst of the lot, and it's now behaving properly after cleaning. Cleaned it several times with deoxit, but it was giving me highly variable readings. It wouldn't settle to one resistance when I pressed the switch. And so what I did to clean it, and this is something that is going to be somewhat controversial and not necessarily recommended, but I took a piece of sandpaper, and this isn't regular sandpaper. This is 2000 grit, so it is very, very fine. In fact, if I touch it, it feels just simply like a smooth piece of paper. What I did is I put this piece of paper between the two contacts, pressed down very lightly, and simply withdrew it. And I did this a few times, like so, pressing down very, very lightly and withdrawing it. And again, on the opposite side to clean the wire. And again, this wire is connected to this here, which then goes to the positive output. So this is how I cleaned the more recalcitrant of the contacts, and now it's behaving properly. This wire may or may not be gold plated, I'm not sure. We don't want to be too aggressive with it and end up removing any plating that's there to protect it from tarnishing. But nonetheless, I do suspect that some of the tarnish that may be on the other surface may indeed have transferred over to gold wire anyway. So I'll just give this another wipe, and then I think we'll be off to the races. And this is as clean as it's going to get. Any more aggressive scrubbing would likely result in damage to the mechanism, and so we don't want that. We just want it to be operational and ready to go back into the instrument, and that's where we are. So we'll reassemble this and go from there. So to reattach this assembly, all we do is position it correctly so that the screws are going through these holes into the actual frame. There we are. My mom and dad used to use this expression a lot. They would say, don't do as I say, or rather, don't do as I do, do as I say. I'm not sure if that applies here or not. But suffice to say, don't do what I just did. I put those brackets in the wrong location. They're actually towards the outside of the instrument. Like so. This is the correct position of these brackets. Well, that's about all there is to the servicing of the electrical components of a vintage Korg MS-20 keyboard. Of course, if we had found any resistors to have been shorted or open, we would have replaced them, but that wasn't the case. You can use a similar approach to service any vintage keyboard, including those with J-wire systems or even those utilizing a diode array. Simply verify that all of the individual components on the Keybed assembly are indeed functioning as they should. Clean all of the keyboard contacts initially without touching them, just simply by spraying on a contact cleaner such as Deoxit, and then identify any key contacts that are intermittent and clean those by very light touch with a very high grit sandpaper such as 2000 grit that you can find in your local hardware store. So that's about all you need. A little bit of sandpaper, some contact cleaner, and a screwdriver, and you too can service your vintage keyboard. What we haven't really covered here today is the servicing of keyboards that use the membrane type approach or other assemblies that can be found on sequential circuits, synthesizers, and some of the later Roland synths. Nor have we covered the mechanical aspects of servicing a keyboard such as this, which might include replacing springs or keyboard bushings, lubrication, and so on. But that'll be for another video. So that's all for today's video. I hope you've enjoyed it and found it entertaining or informative. Thanks for watching. Have a great day.